Let's talk about something we all use every second of every day, but almost never think about. Behind every video you stream, every call you make, there's this hidden world of invisible rules making it all work. Today, we're going to meet the invisible architects of our digital world, communication codes.
You know the feeling, right? You're on a super important call, and suddenly, quirk, the audio just cuts out. Or you're watching a movie, and the screen just turns into this mess of giant blocks. It's the worst. But have you ever really stopped to think about what's actually physically going wrong in that moment? Well, that frustration, that glitch, that breakup, it's all caused by one single villain, and its name is noise. Now, in communication, noise isn't just, loud sounds. It's any interference, any static, any random chaos that gets in the way and tries to scramble our messages as they travel from point A to point B.
So, to understand how we fight this enemy, we first have to understand the battlefield. And that battlefield is called the digital channel. It's the arena where all of our digital conversations happen.
Now, in the world of information theory, the standard model for this is something called a discrete memoryless channel, or DMC. I know, that sounds super technical, but the idea is actually pretty simple. Memoryless just means the channel doesn't care what happened a second ago. Every little bit of information is on its own, independent journey. So here's an easy way to think about it. Just imagine the channel is the room where you're having a conversation. Sometimes that room is a perfect, soundproof recording studio. But other times, it's a loud, crazy, crowded subway station during rush hour. The whole challenge is making sure your message gets heard, no matter how ridiculously noisy that room gets. So, how on earth do we do it? How do we have a crystal clear conversation in a chaotic world? Well, we use a special toolkit. We use codes, powerful codes, that are specifically designed to fight back against all that noise. And the first and most fundamental tool in our kit is the block code. This is really the workhorse of digital communication. Block codes work by taking a chunk of your data, a block, and adding some clever, redundant information to it. But here's the magic. The longer you make that block of data, the chance of an error doesn't just go down, it plummets. It drops exponentially. And that's an incredibly powerful way to make sure your message arrives in one piece. Okay, but what about when that room is just exceptionally noisy, like unbelievably chaotic? For those really tough situations, we need a special tool that can push the absolute limits of what's possible. And that tool is the list code. Think of it like this. Instead of a witness at a crime scene identifying just one suspect, they give the police a lineup of the 3 most likely culprits. A list code does the same thing. The decoder gives you a short list of the most probable messages, which gives us a much, much better chance of finding the right one when the noise is trying to hide it. So, we've got codes for reliability, and we've got codes for really tough channels. But what if you need both of those things, plus you need it to be lightning fast? For that, we turn to the sheer elegance of binary linear codes. The secret sauce here is their structure. These codes are built with a clean, predictable, algebraic foundation. They follow very strict mathematical rules. And because of that, they are exceptionally easy and super fast to decode. For the binary channels of zeros and ones that run our world, these things are just fantastic. And finally, what do you do when the noise isn't just loud, but it's completely unpredictable? Like, the room itself keeps changing shape and volume second by second. For that level of chaos, we have random codes. These use a really clever technique called correlated decoding. What that means, basically, is that the receiver can actually look for hidden patterns within the noise itself. It helps it make a really educated guess about what the original message was. It's the ultimate tool for adapting on the fly. Wild, right? So let's just do a quick recap of our toolkit here. We've got block codes for our general, everyday, noisy channels. We've got list codes for when things get really tough. We have binary linear codes when we need speed and efficiency. And for total, unpredictable chaos, we have random codes. Each one is a specialized solution for a specific kind of problem.
Now, we've spent all this time talking about fighting noise. But what if there is no noise? What if you're in that perfectly quiet, soundproof room? Well, in that case, the entire goal of coding just flips on its head. It's no longer about survival. It's all about efficiency.
And that brings us to our last scenario, coding in perfect, totally noiseless conditions. Here, the art isn't about being tough, it's about being as compact as possible. The tool for this job is called minimum redundancy coding. And notice the key difference here. It has 0 error correction capability. It doesn't need it. Its one and only job is to represent information using the absolute fewest number of bits it possibly can.
You can think of this like data compression, kind of like a zip file. On a discrete, noiseless channel, you don't waste any bits on protecting the message because there's nothing to protect it from. Every single bit is dedicated to one thing, making that message as small and efficient as humanly possible.
So from the noisiest, most chaotic environments to the most pristine and quiet ones, these codes are constantly working behind the scenes. Let's put it all together and see what the journey of a single message actually looks like.
Every message you send goes on this amazing digital journey. It starts as your original idea, the source. Then it gets translated and wrapped in a protective layer of code. That's encoding. It then has to travel through the crazy, noisy world, the channel. But because of that clever code, the decoding process can rebuild it, stripping away the noise, correcting the errors until your message arrives at its destination, perfectly clear and intact.
And that's really the big takeaway here. Whether it's fighting off noise or just being as efficient as possible when there isn't any, these different codes are the invisible, mathematical foundation of the digital world we all rely on every single day. They are the true, silent heroes of modern communication.
So, the next time you have a crystal clear video call, or you're watching a movie and it doesn't buffer even once, just take a second to think about it. What unseen battles against noise were just won? And what invisible architects, what brilliant codes are hard at work in that very moment, just for you?